actually equal to kilogram per meters in second. Okay.
Are those seconds?
Just.
Are those SS or fives?
Yeah, my handwriting wasn't the best one, so. Let's do this again. It's Newton meter, it's kilogram meter per second square, right, is Newton, okay? And then I have Newton per square meter times seconds. So you end up with kilogram per meter in a second. All right, that gave us a Reynolds number of 36,753. Yeah, someone's not done a good job of this.
Mhm.
Okay, so that's turbulent, but whether it's fully turbulent or not depends on the relative roughness, which is what we just looked up, right, in that graph. So it is fine to assume, let me see, so relative roughness was equal to 0.04. That's epsilon over D, okay? That was 2 millimeters over 50 millimeters. So it's fine to assume fully turbulent. Fine to assume in this case. Okay, so our mechanical energy balance, which we have to set up to solve this problem, we have the pressure term plus our kinetic energy term, potential energy, right, our friction, our head loss term, and then shaft work. So I had a question. I actually wasn't sure when you asked me last time whether or not the shaft work on this side was negative or not in the equation, and it is. Okay, so the actual equation does have a negative, and why they decided to put it on this side, I have no idea, right? Because in my opinion, it's easy to add up all the energy on this side and just go plus equals 0. The key is, so depends on your book. Some thermo books thinks that work that you get out of a turbine is actually a positive thing. So in the energy balance, they add a negative in front of the W. Okay, it's easier for me at least to think about this overall. You don't have to think about sign. Okay, if energy goes into the system, it's positive. If it comes out, it's negative. It just means that your turbine work will have a negative in front of it. Okay, so that is what the book is following. Okay, the negative here means that if you have a pump, this number here is positive. Okay, I promised you I will not put a pump on the exam because we haven't looked at that. We haven't covered that. Okay. All right, but we have no shaft work, so it's equal to 0. Okay. Now, what else do we need? So what about this term? What's delta U? In this, remember our system is this.
Just U?
Oops. Is it just U? 0. Okay, so delta U squared equals U2 minus U1, and it's equal to 0. Because whatever goes in here is coming out here, right? It's an incompressible fluid, so even if we have a pressure change, the volumetric flow rate doesn't change. Okay, now, we're looking after the hole right now, right? Because once the hole opens up, obviously, whatever comes in here, some of it goes out here and some continues. But to calculate the pressure at this point, let's not do that. Even after the hole, whatever goes into this pipe, right, is gonna come out on the other end. All right, delta P. And delta P is equal to P2 minus P1. Okay, pressure here minus there.
Are you doing gauge or absolute?
So that's your choice in this case. You can keep delta P and just calculate what your delta P is. The other thing you can do is say that this is equal to negative PG. And so what that will give you is the gauge pressure up here. It's negative in this case, the way we're looking at it. The delta P is negative because the pressure is higher here than it is here. Okay? So as long as you can give me the gauge, you can give me, tell me that this is such and such gauge pressure. Or you can tell me it's absolute. Just don't mix them up. Okay? Don't tell me it's absolute pressure and then you give me the gauge pressure. Bottom line. Okay? Now we need the gauge pressure for B, for part B, so we might as well calculate the gauge, right? Okay, delta Z.
0.
0. We have no, right? There's no elevation change from there to the other point. Okay, so our head loss term, what do we have? Let me just put it all up there and then we'll step through one by one. Okay, so in general, we have KF equals KF entrance. Okay, do we have an entrance term?
No.
No. There is not an entrance term because the radius before is equal to the radius after. So in this case, this is equal to 0. Then we have KF pipe. Okay, and we have 5 plus 4 meters of pipe. Okay, that's our L. Okay, then we have KFT and a KF valve. I'm not supposed to say valve. And KF exit. Okay, do we have an exit term?
Probably, yeah.
Yeah, because it opens up into the tank. So there is an exit term, that one is equal to 1.0. Our KF pipe.
Is that always?
Yes, for the exits so for normal exit, there are some other things in the book, but for most occasions that's what we're gonna use.
So if the valve is closed, would we not have an exit term and we wouldn't include
So if that valve is closed, there would be no flow.
oh, we,
So then there's no friction loss because there's no flow. Right. So, the time you would not have an exit term is if you're looking at a pipe like this and you're right, it continues. You're trying to, this is your 1 and this is your 2, and for whatever reason you're setting up an energy balance across here. But if this continues to whatever another tank, then you wouldn't have an exit term there. Okay, so our pipe is our 4FL over D, where we went from here saying that it's fine for us to assume fully turbulent. By the way, it's perfectly fine for you to read this F from the graph, okay? If you don't want to take the time and and calculate this. This will give us an F of, right, we said that E is 2 millimeters and our D is 50 millimeters, 5 centimeters. That gives us an F of 0.01617.
Do we have to use the graph, or can we do?
You do not have to use the graph. If you're more comfortable with this, it's not a, right, it's not a bad equation. And obviously, if you use the graph, you have to have the Reynolds number, right? So that's that's one. So in other words, you can only do that if you know the linear velocity for the pipe. Now, if you were not assuming fully turbulent flow and you were using this equation for F, 1/3.7, 7/d, that's where we have 1.255 Reynolds number. If you were to use this one instead to get it more accurate, right, you put that in there and then you do that a few times, you get that F is equal to 1.634. Okay, so use 1.6, which is probably, right, 1.6 is probably the best you will get from the graph. I would say we're close enough. Okay, this would be the more accurate value, right? But I wouldn't expect you to do that on the exam. Okay, unless your conditions is such that you cannot, right? If you remember the graph, it looks like this, right? And we were here is where you have fully developed turbulent flow. Here is where F is not changing. If you're down in this region, right, over on this side, then you do need to use this equation, okay? I wouldn't expect you to do all those calculations on the exam, but I would expect you to tell me how to do it, right? In other words, you would, right, we would guess a velocity, calculate a Reynolds number. From the Reynolds number, we'll use this equation first, calculate a new U, go back and see, are we at fully turbulent conditions or not? If not, right, you have a beginning F. You can calculate a better value from here by going back and forth a few times. And continue until the U that you put in actually matches the U that you calculate in your equations. Okay. We don't have to do that in this case. We have KF pi is 4 times 1.61. Okay, I used the 3/4 since I had it. 10 to the -2 times our 9 meters of pipe over 0.05 meters. That means that our KF pipe is 0.7581. And then we went in and looked at all the fittings so you know where these numbers are from. We have a KFT that was run through, flanged, and it's 150 over the Reynolds number plus 0.501 plus 1 over the inner diameter of the pipe in inches, which is 1.97 inches, 5 centimeters in this case. If we put in our Reynolds number, 36,700, this number for the T, oh, oops, hold on, wait. This is the number for the T, sorry, 7581. The head loss for the pipe is actually much more than that. It is 11.76. Okay, sorry about that. Okay, that was the T. We're working over here. KF valve, which is equal to 300 over the Reynolds number plus 0.10 and plus 1997. That one is equal to 0.1590. And our delta P over rho that we have, what did we say? This one is equal to 0, this one is equal to 0, and this is negative KF T squared over GC. Okay, if we add up our sum, KF then is no entrance term. We have our pipe term, which is 11.76 plus 0.7581 plus 0.1590 plus 1.0. And that is equal to 13.6818.
Why is it in inches for KT?
So this is the what they have determined, okay? It's by definition in the equation, okay? Please make a note of that. It says the equation has a K1 over the Reynolds number, so this is general for fittings, plus K infinity, 1 plus 1 over ID, and it has an inches over here. So
Oh,
this,
units of in-
whatever parameter here relies on you having done this in inches. Blah, blah, blah. Okay, so that's our total head loss. Our delta P then is equal to negative density, kilograms per cubic meters, times our head loss, which is 13.6818, times 0.4244 squared, and 2 times 1.0 our kilogram meter second square newton. That is equal to minus 1.067 1,000, sorry, 0.5 pascals. So, pressure, it's negative because our P2 is smaller than our P1. So you can tell me that it is 1.1 kilopascal gauge, right? Or you can tell me that P2 is equal to 101.3 plus 1067, which is about 102 kilopascals. Okay, so just to make sure, this is absolute. Yes, question. Oh, thank you. Good observation. This is our P1, that's what we were asked for. Yes.
P2 is
P2